Welcome to Lacea class. I am your teacher, John Lacea.
A blessed day to everyone! Today, we are going to learn neural network binary classification. An artificial neural network, or ANN, is based on a collection of connected units or nodes called artificial neurons, which loosely model the neurons in our biological brain. Each connection, like the synapses in a biological brain, can transmit a signal to other neurons. An artificial neuron receives signals, then processes them, and can signal neurons connected to it. Artificial neural network is a mathematical function that maps a given input to the desired output. To understand what that means, let us take a look at a single-layer neural network known as the perceptron. This mathematical formula is a perceptron that takes in a set of inputs, performs some mathematical computation, and outputs the results of the computation. The mathematical function y hat is equal to the summation of the product of w sub I, which is the weights, and x sub I, which is the input, to be added to the y-intercept or the bias. The graph shown to the right is the visual of this mathematical function. We can see that there are three inputs, namely x sub 1, x sub 2, x sub 3, and then the first layer has a weight w1, w2, w3. It will be multiplied with that x sub 1, x sub 2, x sub 3, and then the result of that summation will be added to the bias. In addition to that, it will also apply activation function so that the neural network model can be able to learn complex patterns from the data set. And then it will output the target variable y. A multi-layer perceptron, or MLP, is an artificial neural network widely used for solving classification and regression tasks. Multi-layer perceptron consists of fully connected dense layers that transform input data from one dimension to another. It is called multi-layer because it contains an input layer, one or more hidden layers, and an output layer. The purpose of a multi-layer perceptron is to model complex relationships between inputs and outputs, making it a powerful tool for various machine learning tasks. Neural networks with many hidden layers such as 10, 100, 1000 are considered deep networks, and their application is called deep learning. Moreover, having more than one hidden layer helps in achieving a high nonlinearity. We want to achieve a high nonlinearity because without it, a neural network would be a giant linear function. The machine can learn complex patterns from the dataset, from the given dataset, if it is a nonlinear. The key components of multi-layer perceptron are the following. First, it must have an input layer. Each node, or also called as node in this layer, corresponds to an input feature. For instance, if you have three input features, the input layer will have three neurons or three nodes. Second, it must have hidden layers. A multi-layer perceptron can have any number of hidden layers, with each layer containing any number of nodes or neurons. These layers process the information received from the input layer. And then finally, we have the one output layer. The output layer generates the final prediction or classification or the result. If there are multiple outputs, the output layer will have a corresponding number of neurons. This diagram shown here shows the representation of a fully connected nature of a multi-layer perceptron. This means that every node in one layer connects to every node in the next layer. As the data moves through the network, each layer transforms it until the final output is generated in the output layer. We can see that the output layers consist of two classification values, but only one will be selected at the final end. The meaning of the training the neural network, it means that it is a process of fitting a model to a data set. It is also the process of fine-tuning the weights and biases from the input data. During the training of the machine, applying the neural network, each iteration of the training process consists of the following steps. Calculating the predicted output y hat or z, known as the feed-forward or forward propagation. Next to that, updating the weights and biases, known as the back propagation. And then, in this diagram will tell us that during the training process, it will repeat and repeat, performing the feed-forward or forward propagation, and as well as the back propagation. Training a neural network basically means calibrating all the weights by repeating two steps, forward propagation and back propagation. In forward propagation, we apply a set of weights to the input data and calculate an output. For the first forward propagation, the set of weights values are initialized randomly. Whereas the back propagation, we measure the margin of error of the output and adjust the weights accordingly to decrease the error made by the machine during the classification or predicting in the training process. Neural networks repeat both the forward and back propagation in an iteration until the weights are calibrated to accurately predict an output. And it will only stop if the margin of error or the loss already achieved the threshold. Multi-layer perceptron rely on optimization algorithms to iteratively refine the weights and biases during the training. Popular optimization methods include the stochastic gradient descent, that it updates the weights based on a single sample or a small batch of data. This is the formula of the stochastic gradient descent. Another optimization to refine the weights and biases is the ADAM optimizer, an extension of the stochastic gradient descent that incorporates momentum and adaptive learning rates for more efficient training. The math formula of this ADAM optimizer are the following. An activation function is a function that it is added into the artificial neural network in order to help the network learn complex patterns in the data. We want that our neural network model achieve nonlinear. Activation functions are applied at the hidden layer of a neural network. The purpose of an activation function is to transform the input signal into an output signal. They are necessary for neural networks to model complex nonlinear patterns that simpler models might miss. We need nonlinearity so that our model can learn complex patterns. Some of the major activation functions are the following. We have the sigmoid, the hyperbolic tangent, and then the rectified linear unit or the ReLU. Let us look at one additional aspect of neural networks, the learning rate. Learning rate helps us in building trust in our decision of updating the weights. For example, while deciding on the magnitude of weight update, we would potentially not change everything in one go, but rather take a more careful approach in updating the weights more slowly. This results in obtaining stability in our model. We wanted to train the machine to learn slowly by slowly, in a slow pace, just like human beings. Most especially if we are a slow learner, we need to study the subject slowly and slowly. A lower learning rate is always preferred. However, note that a lower learning rate would result in a longer time or more iteration during the training process to get the optimal results. The recommended value for the learning rate is the amount of a very small decimal value, which is 0.001. And then we pass that value when we instantiate a object using now the ADAM optimizer. And then when we compile our neural network model, we pass that object ADAM. And then a learning rate of 0.001 will make the machine train slowly and slowly so that the machine can be able to learn the complex patterns from the data set. Not that very fast because most of the time, fast learning may not be always effective. In classification, the output is bound between 0 and 1. In the case of binary classification, the output layer would have 2 nodes instead of 1 in the output layer. One node corresponds to an output of 0 and the other corresponds to an output of 1. There are issues in computing the outputs that it has values that are greater than 1. In other cases, the values could be also less than 0 or out of the range. The purpose of the softmax, which is a activation function, is to normalize the values, ensuring the sum to 1 and are within the range from 0 to 1, allowing them to be interpreted as probabilities for different classes. We can place the softmax activation function when we add a define now the output layer. In this example written in Python code, the last add of a layer command is the output layer, and we want to make sure that the output will fall within the range from 0 to 1. When we will be applying the softmax, we apply the softmax if we find out that the predicted value is out of the range from 0 to 1. And that's the time that we use the softmax. The advantages of multi-layer perceptron are the following. Versatility. Multi-layer perceptron can be applied to a variety of problems, both classification and regression. Next, nonlinearity. Thanks to activation functions, multi-layer perceptron can model complex nonlinear relationships in data. And then the third, parallel computation. With the help of graphics processing unit or GPU, multi-layer perceptron can be trained quickly by taking advantage of parallel computing. However, the multi-layer perceptron neural network model is not perfect. It has weaknesses or disadvantages. Number one, it is computationally expensive. Multi-layer perceptron can be slow to train, especially on large datasets with many layers. Number two, it is prone to overfitting. Without proper regularization techniques, multi-layer perceptron can overfit the training data, leading to a poor generalization or poor classification prediction. And then finally, multi-layer perceptron is sensitive to data scaling. Multi-layer perceptron require properly normalized or scaled data for optimal performance. If we do not scale the data, it will affect the performance of our neural network model after the training. Let us learn how to determine the size of our neural network model. A neural network is characterized by the number of layers, which is the depth of the network, and the number of neurons in its layer, which is the width of the layers, and the type of layers. In this previous example, the previous slide, we have the dense layer of a fully connected neurons, and as well as the activation functions used. There are other layers types, such as the dropout layer, that can increase the network's ability to generalize by randomly dropping connections between layers during the weight updates. Another type of layer is the conv2d layer that enables us to build convolutional neural networks that excel at image processing. If we train the machine to detect objects using images or videos. When designing a neural network, how do you pick the right number of layers and the right number of neurons for each layer? The short answer is that the right width and depth depends on the problem that we are trying to solve, the dataset that you are training with, and the accuracy you desire. As a rule, you want the minimum width, which is the number of neurons, and then the depth, which is the number of layers required to achieve that accuracy. And you get there using a combination of intuition and experimentation or experiment through trial and error. That said, here are a few guidelines to keep in mind. The greater widths and depths give the network more capacity to learn by fitting more tightly to the training data. They also increase the likelihood of overfitting. It is the validation or test results that matter, and sometimes loosening the fit to the training data allows the network to generalize better. The simplest way to loosen the data is to reduce the number of neurons to make it fit, avoiding overfitting. Generally speaking, you prefer greater width or many neurons or nodes to greater depth, in part to avoid the vanishing gradient problem, which diminishes the impact of added layers. The rectified linear unit or ReLU activation function provides some protection against vanishing gradients, but that protection is not absolute. In addition, a network with, say, 100 neurons or nodes in one layer trains faster than a network with 5 layers of 20 neurons each, because the former has fewer weights. Think about it. There are no connection between neurons in one layer. but there are 1,600 connections between 5 layers containing 220 neurons each. Fewer neurons means less training time. State-of-the-art neural networks trained with large datasets sometimes take days or weeks to train on a high-end graphics processing units. So training time is important. In real life, data scientists experiment through trial and error with various widths and depths to find the right balance between the training time, accuracy, and the network's ability to generalize. For a multi-layer perceptron, you rarely ever need more than 2 hidden layers, and one is often sufficient enough. A neural network with 1 or 2 hidden layers has the capacity to solve even complex nonlinear problems. 2 layers with 128 neurons each, for example, gives you 16,384 weights that can be adjusted plus 256 biases. And that's a lot of fitting power. You apply this if we have a complex dataset. Experiment by starting with 1 layer at most, and then later on you experiment with 2 layers of 512 neurons each. And then you need to divide that 512 and then the width or depth until the validation or test accuracy drops below to an acceptable threshold. So we can experiment through trial and error. We can start with a 1 layer. We can choose 512 neurons and then train the machine. And if it did not satisfy our required performance of the validation or test accuracy, we can reduce that 512. We get the half of that and then retrain again the neural network and then compare the result of the validation or the test accuracy. The meaning of the training set is used to train the model where it learns patterns and relationships from the data, whereas the test set is used to evaluate the model's performance on completely new data, providing an unbiased measure of its generalization ability. So the training set is a data set used to train the machine to learn patterns and relationship, whereas the test set, after the training of the machine, we will test the neural network model to predict or to classify on a new data that the machine did not seen it before during the training to test. The meaning of testing or test or validation performance evaluation, it refers to assessing how well a trained model performs on a separate dataset of unseen data, the test set. Whereas the training performance evaluation refers to monitoring the model's performance on the data it is actively learning from the training set during the training process, allowing for adjustments to improve its learning trajectory. Essentially, the testing or validation accuracy evaluates the model's ability to generalize to new data, while the training performance evaluation helps optimize the learning process itself. How we can tell if our neural network model's performance after the training is overfitting, underfitting, good, or very good? We simply compare the scores or grades between the testing or validation and training. Overfitting occurs when the training is high, but the testing is low or lower, and then the gap is greater than 5%. Overfitting means it refers to the learning the training data too well at the expense of not generalizing well to new data. Look at this graph below. This graph shows that the training accuracy is perfect 100%, but the testing accuracy is 85.71%. So this is overfitting. Even though we got perfect to classify or to predict after the training, but when we test our neural network model, testing with a new data never seen it before, it got low, 85.71%. Thus, overfitting performance is not a good performance. So when the training accuracy is greater than the testing accuracy, and then the gap is greater than 5%, we can now judge that the performance of our neural network is overfitting. Underfitting, on the other hand, refers to failing to learn the problem from the training data sufficiently. Underfitting occurs when both the training and testing are very low scores, like below 75%. This graph shows that the training is 60% accurate, and then the testing is 63% accurate. So if we have this basis of judging a underfitting, that if both the training and then the testing accuracies are below 75%, we assign that as the passing grade or score. Therefore, it is underfitting, and underfitting is a bad performance similar to overfitting. How do we tell if our neural network model is good or very good? We can judge the neural network model performance a good or very good if both the training and testing scores are greater than 75% or even equal to 75%. Just like this example graph above, the training got a grade of 96.77%, and then the testing got a perfect score or grade of 100%. So we can judge that our neural network model is good. Let us study a good example of neural network binary classification, which is the heart disease classification. The heart disease dataset has 39 samples or 39 records of persons or people. 26 samples or persons are healthy, while the remaining 13 persons are diagnosed with heart disease. The table shows the 12 attributes of the heart disease data set. The first is the age of the person, which is a unit of measurement in years. Next is the sex or the gender of the person. A value of M denotes that it is a male. A value of F denotes that it is a female. This sex is a string attribute or a categorical attribute. Next is the chest pain type. It has 4 possible values. We have TA stands for typical angina, ATA, atypical angina, NAP, non-angina pain, and then ASY, asymptomatic. And it is a string attribute or a categorical attribute. Next to that, we have the resting blood pressure, and then the unit of measurement is millimeters of mercury. Next is the serum cholesterol, and then the unit of measurement is the milligrams per deciliter. Next attribute is the fasting blood sugar, that it has two possible values, either 0 means less than 120 milligrams per deciliter, or A1 meaning greater than 120 milligrams per deciliter. Next attribute is the resting electrocardiogram results. A value of normal, meaning it is normal. A value of ST, meaning it is a ST-DUST wave abnormality. This resting electrocardiogram results is a string attribute or categorical attribute. Next attribute is the maximum heart rate achieved. The values will fall within the range from 71 beats per minute up to 202 beats per minute. Next attribute is the exercise-induced angina. The meaning of exercise-induced angina, it refers to chest pain or discomfort that occurs during physical activity or exertion due to reduced blood flow to the heart muscle. A value of N, meaning there is meaning it is no chest pain or discomfort. A value of Y, meaning yes. It is a string attribute. Next attribute is the old peak. And then this old peak is ST, depression induced by exercise relative to rest. And then next attribute is the slope of the peak exercise ST segment. A value of up means up sloping. A value of flat means it is flat. And then the final attribute is the target variable heart disease. That it is now the classification target variable that it contains two possible values. A value of no, meaning that the person is healthy or normal. A value of yes, meaning that person has a heart disease. If we open up the heart disease dataset, it will look like this. It has a records of 39 persons or individuals or people, and these are the records of the individual person. Let us learn now the code written in Python, how we can apply neural network binary classification to predict an individual if it has a heart disease or not. Let us study the Python code for implementing the neural network binary classification. First, we need to install some Python package libraries such as the pandas, numpy, scikit-learn, imblearn, matplotlib, seaborn, pickle, tensorflow, and h5py. The TensorFlow is the library that provides us neural network binary classification. Next, we need to write now the import commands to load them. And then we are going to use them and ready to be used in our latter part of our Python codes. At cell number 3, we are going to load the heart disease dataset that consists of 39 samples using the pandas library command read underscore CSV. And then after that, we verify and print the names of the features or the column of that heart disease data set. And we can see them, the names, such as the age, the sex, chest pain type, resting blood pressure, cholesterol, fasting blood sugar, resting ECG, max heart rate, exercise angina, old peak, ST slope, and then the target variable, heart disease. After that, we are going to display a descriptive statistics, and we can see that the youngest person in that 39 samples has a age of 32 years old, and then the oldest has a age of 65 years old. Next, at cell number 5, we define a method named remove duplicate samples, that the purpose of this is that it will delete or remove records that have duplicate records. At cell number 6, we need to check if there are some duplicate samples or records using that pandas library command, duplicated, and then we compute how many duplicate samples, and then the result is none. At cell number 7, if there are some duplicate records, we are going to call the method remove duplicate samples. At cell number 8, we are going to check for possible not applicable NA values using the pandas library command is NA, and then we calculate how many of them. So far, there is none. If in case there are NA values, we need to replace them either by computing first the mean or the mode of that column, and then whatever the amount calculated, that will now be the value to fill and replace NA values. At cell number 9, we are going to check if our dataset has a null or a missing values, and then so far there is none. But if in case there are some, we need to fill those missing values or null values either by computing first the mean or the mode. And whatever the amount computed, that will be the value to replace or to fill that null or missing values. At cell number 10, we are going to check if there are columns that contains a string or categorical variables. And there are 6 categorical or string variables, namely the sex, chest pain type, resting ECG, exercise angina, ST slope, and then the target variable, heart disease. Later on, we are going to convert those string values into a number. At cell number 11, we are going to display the histogram of every columns or features within our data set to simply check if our data set approaches normality or normal distribution. And then this is the histogram for the age, and it is approaching a bell-shaped curve, and then followed by the sex, chest pain type, resting blood pressure, cholesterol, fasting blood sugar, resting ECG, max heart rate, it is a skewed curve, exercise angina, old peak, ST slope. At cell number 12, we are going to convert the string values of the target variable name, heart disease, and I did not implemented the label encoding or the one-hot encoding. Why? Because it is a target variable. And then since the values no or yes of that heart disease is no ranking or there is no order, we are not going to apply the label encoding. And since it is a target variable, we are not going to apply as well the one-hot encoding because the one-hot encoding will add more columns in our data set. But the target variable must only have one column. So we can use the pandas library command to convert no into a value of 0, yes string into a numeric value of a 1. And then after that, we print to verify. And if we look at now the final values of the heart disease, no longer we can not see any more values of no or yes. They are being replaced by either 0 or 1. At line number 13, we are going to display another graph called the box plot to identify columns or features that have outliers. The age has non-outliers. The sex has a 1 outlier. The chest pain type has 3 outliers. The resting blood pressure has 2 outliers. 3, 1, 2, and 3. Those tiny dots outside the whiskers of that box plot. The cholesterol has 2 outliers. The fasting blood sugar has 2. The resting ECG has none. The max heart rate has none. The exercise angina has 2 outliers. The old peak has 3 outliers. And then finally, the ST slope has 1 outlier. I decided not to remove those outliers identified. Why? Because we only have a very small data set consisting of only 39 samples. At cell number 14, we are going to apply the Pearson correlation to determine some columns or features if they are correlated with the target dependent variable named heart disease. Only this Pearson correlation will only apply to those columns or features that contains numeric values such as the old peak, resting blood pressure, the age, fasting blood sugar, cholesterol, and then the max heart rate. The old peak has a high, we can say it is a 63% correlated to the heart disease. Whereas the rest has a small correlation towards the heart disease. At cell number 15, again, we are going to print the names of those 6 string or categorical columns or features or variables. And here they are once again. And then at cell number 16, we are going to convert those 6 identified string columns or features using the one-hot encoding. Because the one-hot encoding, we apply this whenever the values are having no ranking or in not particular order. And then after we implemented the one-hot encoding, we verify by printing them out. For example, the sex added 2 columns for the female and male, whereas the chest pain type that has 4 possible values, it added 4 more columns in our data set. We have a column for the ASY asymptomatic, ATA, NAP, and then the TA. And also with the other categorical or string variables, they too have added additional columns. At cell number 17, we are going now to decide what are those independent columns and what is the dependent column. So all of those columns except the heart disease are chosen to be the independent variables or the predictors for predicting a heart disease. So I stored them into a variable named X, and whereas the heart disease will now be our target variable, and I store it into a variable Y. After that, we are going to go to line number 19 to determine how many samples for those persons who are healthy, for those persons who have the heart disease. And we can see that there are 26 persons who are healthy and 13 persons who got the heart disease. And we can display a graph to more visualize the number of samples for every category of the heart disease, either a category of no or a category of yes. Knowing that, we describe that there is a imbalance of classification. The effect of imbalanced data set is that the neural network model may be biased toward the majority class, impacting the predictive performance for minority classes. To solve this issue, we are going to use the package library known as the SMAT. And then what does this SMAT will do is that it will balance the dataset by adding samples using oversampling technique. And if we implement this SMAT, now the number of the persons who are healthy, which is 26, matches now with the number of persons who got a heart disease, which is 26. Now the classification number of samples are now balanced. At cell number 22, we are going to split our data set into two, the training set and then the test set. 80% of the data set will go to the training set, while 20% of the data set will proceed to the test data set. So the training size will now be approximately 31 samples, while the test size will now be 8 samples. Next, at cell number 23, we are going to implement the standard scalar. Why? The standard scalar is applied when the characteristics of the input dataset differ greatly between their ranges, or simply when they are measured in different units of measure. For example, the age has a range from 32 to 65 years old, while the fasting blood sugar has a range from 0 to 1 milligrams per deciliter. As these two columns are different in scale, it will affect the training performance of our neural network model. That's why we are going to standardize using the standard scalar to have a common scale. So we are going to standardize the input variable X. Those 11 columns from age until to that old peak will be having a common scale. At line number 24, we are going to save that standard scalar object for future use. At cell number 25, we are going now to set up the sizing and setup for our neural network binary classification. The TensorFlow API library command sequential is what we are going to implement. And as I said before, the size of our neural network will only consist one single hidden layer. And then I set the one lone single layer to have 10 neurons. The dense layer implemented here as a hidden layer is a class that represents a fully connected layer with a specified number of neurons. And then I implemented the rectified linear unit or the ReLU as a activation function. and then I pass the 11 columns or features to be the input for our hidden layer. The dropout added for the hidden layer can increase the network's ability to generalize by randomly dropping connections between layers during the weight updates. The output layer, again, we implemented the dense layer, will only have one neuron. Even though we know that the heart disease can classify either no or yes, healthy or it has a heart disease. We need to place only one neuron as the output layer. And then the chosen activation function for the output layer is not the softmax but the sigmoid, because there is no problem of classifying the values that it will fall within the range from 0 to 1. I implemented the optimizer named Adam with a learning rate of 0.001. And then we are ready now to train our neural network model using the compile command and then pass all those arguments. At line number or cell number 26, we set up a callbacks for our TensorFlow that the callback is that it will stop the training if and only if the amount of the error or the loss reaches the minimum. The minimum or the threshold is 0. So if the machine during the training achieve a none or a 0 loss or a 0 error, that means that the machine did not committed any mistakes. Therefore, we stop now the training process. At cell number 27, we are going now to call now the pit command to start now the machine training. I set the number of epochs to 600, the number of iteration during the machine training. And then the result, we can see the training result listed here begins at epoch number 1 and it goes to epoch number 2. And as the epoch goes by or the iteration goes by, the amount of the loss or the errors decreases. This loss or the error is the mistakes made by the machine when it tries to analyze the complexity of the data set. And then at the end of that, when it reaches the last epoch or the iteration, which is 600, the amount of loss reaches an amount of 0.0914, which is near to our ideal threshold of 0. And probably if we increase the total epoch to more than 600, like 700 or 800, that loss will be smaller and smaller, and it will reaches a limit of a 0, the ideal loss or number of error. At cell number 28, after the training is finished and also the validation is also tested out, we can display a graph for the training and validation accuracy and loss. Here, the x-axis will tell us that there are 600 iterations during the training. The y-axis will tell us the accuracy, the training accuracy. And then the validation or the test accuracy of our machine. So we can see that the brown curve is the loss. So during the start of the training at epoch number 1, the machine made a lot of errors or mistakes during prediction or classification. But as time goes by, when that iteration reaches the final iteration of 600, the loss goes smaller and smaller, and it goes to that amount of 0.914 as we saw a while ago. As the number of loss decreases, the number of accuracy increases. This blue accuracy began from a small amount, and it increases and increases until it reaches the highest amount of 1, which is a perfect 100%. At cell number 29, we can also draw a graph that it will only show the training and validation accuracy. So the training accuracy, brown curve, and then the validation accuracy or the testing accuracy, the dotted light blue, will tell us that when we train the machine from starting epoch of 1 until 600, the training and validation accuracy got a small amount, and it increases and increases until it reaches the perfect accuracy of a 1. At cell number 30, we can display this classification report, and then we focus our classification report, which is the F1 score. The F1 score is the overall measure of the model's performance. It provides a single metric that combines both the precision and recall, and it balances the trade-offs between the two. The F1 score, we can see here that we have a 1, which is the perfect score of 1. So classifying a category of 0 got a 1. Classifying a category of 1, which is yes, got a 1. So the F1 score is good because it got a perfect of a 1. We can also see here that the model accuracy after the testing is 100%. So this F1 score is a accuracy after the testing. At cell number 31, we can also display the classification report during the training, and then the classification report accuracy during the training is 100%. The F1 score also got a perfect score of both 1 for classifying a 0, no, and classifying a 1, yes. At cell number 32, we can display now the performance of our neural network model in a graph, in a bar graph. So here in this case, the training and then the testing got both a perfect score of 100%, which is, we can say, very good. At cell number 33, we can also display one classification matrix called the confusion matrix. Here is the graph of the confusion matrix after the testing. A confusion matrix is a table showing the actual versus the predicted outcomes, and it can be used to determine the accuracy of the model. Here in this case, since we know that the model accuracy after the testing is 100%, so the machine did not made any mistakes. It got a perfect classifying no or yes, and there is no errors during classifying a false positive and a false negative. We can also display the classification matrix, the confusion matrix after the training, which is this one. Since we know that it is a perfect score of 100%, therefore we can guess, we can tell that the machine did not made any mistake of misclassifying a no or a yes. It got a perfect score of classifying correct negative and correct positive. He got no mistakes when classifying false positive and false negative. Next to that, we display another classification matrix known as the area under the receiver operating characteristic curve, or the ROC curve. Here is the ROC curve after the testing. We can see that the brown curve reaches the limit of A1, which is the ideal value that our curve will reaches, since it is a perfect score. The diagonal dash blue line is the threshold. Above this threshold, we can say that our model performs well in classifying true positive rate. We can also show the ROC curve after the training, since we know that it got a perfect 100%. Therefore, the brown curve reaches the limit of A1, that it is perfect. At cell number 40, we save our neural network using the H5Py library for future purposes. For example, we can develop another app that the user can input the age, the sex, the chest pain, and with the click of a button, we can predict or classify whether that user is healthy or got a heart disease without retraining the machine, because it is time consuming. So we simply save our neural network, and then it contains now the weights computed in that file. At cell number 41, we are going to load that model being saved just to test. At cell number 42, we are ready now to test our neural network binary classification model by defining a data frame, a pandas data frame, and then here are the inputs that we are going to predict. The age is 40, the sex is male, chest pain type is ATA, the resting blood pressure is 140, cholesterol is 289, fasting blood sugar is 0, resting ECG is normal, max heart rate is 172, exercise angina is no, old peak is ST slope 0, ST slope is up. At cell number 43, we are going to determine if there are string or categorical variables, and there are. Therefore, we are going to convert those string values into a number using the one-hot encoding. And then after that, before we are going to classify or predict, we need first to standardize using the standard scaler. And then after that, we call the command predict to predict now based from that input data. And then the result is it is negative of heart disease. And then the machine has a level of confidence of predicting a negative of heart disease, which is 98.82%. However, there is a chance that this negative of heart disease prediction, it has a chance of 1.18% chances that it can be wrong. So that is now the Python code implementation of the neural network binary classification. I conducted a laboratory experiment by training the machine several times. I started by implementing a single layer or one hidden layer only with 5 neurons and a total iterations or epoch of 600. The results are the following. with a one hidden layer consisting of 5 neurons with a total of epoch, the performance is good. And then we can see that the training accuracy is 95.12, the testing accuracy is 100, and then it uses the entire iteration of 600. When I increase the number of neurons per layer, which is from 5 to 6, the performance seems overfitting because the training accuracy is 95 and then the testing accuracy went low to 90. But if we base it from the lecture that I explained, if it is greater than 5% gap, that would be overfitting. But it seems that it is not overfitting. It is not yet greater than 5%. But the training process early stop at iteration number 586. And if we increase the number of neurons to 7, the performance went well. And then the number of iteration used is 600. And if we increase to 8, the performance seems the same with that number of neurons, which is 6. And if we increase the neurons to 9, the training accuracy went to 95 again, and then the testing accuracy is perfect. I wanted to get a perfect training and testing accuracy of 100%. So I keep doing a trial and error laboratory experiment. By the time that I set the number of neurons to 10 with the same number of hidden layer, which is 1, and then a total epoch or iteration of 600, I finally got what I want in my neural network performance, and that is having a perfect grade or score of 100. And when I jump to a higher number of neurons, such as 20 and 30, still the performance is perfect, 100. However, as we learned in the previous topic that we need to have a right balance between the width and then the depth. That's why I choose this size of a neural network that I will only implement a single layer, not 2 layers or 3 layers, only 1 layer only, 1 hidden layer only, with 10 neurons and a total iteration or epoch of 600. And if I choose 20 or 30, it will be overkill. It will take longer training time if I choose 20 or 30. So the right sizing of my neural network is when the time that the training performance and then the testing or validation performance got a perfect score of 100. And I observed that as the number of neurons increases, the neural network model learns faster. Now, even though that the neural network model got a perfect score of 100, I do not have a self-confidence or overconfident that my neural network will always classify or predict accurately, because all neural network or all models are not perfect. There will always be a mistake in classification prediction because it is not perfect. Now, the results are subject to change when you retrain the machine several times. The training and testing model accuracies will change. Why? Because most algorithms implemented stochastic or randomness. In that forward propagation, during the first forward propagation, the weights are initialized randomly. So every time that you train, it will have different values initialized. And then at the end of the training and testing, you will uh, notice that the accuracy values uh, are not fixed. It will be subjected to change. I studied and tested several machine learning classification algorithms with the same data set, which is the heart disease data set, containing 39 samples. This table shows the performances of the different machine learning classification algorithms. The first machine learning classification algorithm, decision tree, has a good performance. Random forest is also good. Support vector machine is overfitting. The k-nearest neighbor is good. The Gaussian naive Bayes is overfitting. The logistic regression for binary classification is also good. And then the neural network binary classification is very good. I choose very good because it got a perfect score, both the training and testing, which is 100%. And again, the results are not fixed. When you train and train several times, the performance values are subjected to change.
That ends our topic for today. I hope you are inspired in my class. Thank you for watching. God bless us.